All right, today we are going to tackle one of the absolute strangest and maybe most powerful ideas in all of physics, quantum entanglement. What Einstein famously called spooky action at a distance isn't just some weird thought experiment anymore. It's actually becoming the foundation for our future. So, let's dive in.
So let's just start with the question that gets right to the heart of it all. Just imagine for a second, two particles created at the same time that are forever linked. What you do to one particle is instantly, and I mean instantly, felt by the other. It doesn't matter if it's across a lab bench or all the way across the galaxy. This sounds like sci-fi, I know, but it's the bizarre reality of the quantum world.
And hey, if that idea sounds a little unsettling to you, well, you are in great company. That's what the man himself, Albert Einstein, called it, spooky action at a distance. He found it so completely bizarre, so counterintuitive, that he was convinced quantum mechanics had to be missing something. But what if that spookiness is actually the key to a whole new generation of technology?
Okay, so what is this spooky connection, really? Let's define it.
So here's the formal scientific definition, and I want you to focus on that phrase, a non-classical correlation. That's everything. It means these particles are connected in a way that just does not happen in our normal, everyday world. The state of one is fundamentally locked to the state of the other. You literally can't even describe particle A without at the same time describing particle B.
You know, to put it a bit more simply, just think of it like this. It's like two particles sharing one single identity. They aren't really two separate things that just happen to mirror each other. In a very real way, they are two parts of the same unified quantum system.
And this slide, this is perfect for understanding why this is so weird. On the left, you've got a classical connection. Think of two gloves in two boxes. If you open your box and find the left-hand glove, you instantly know I have the right one. But that was always the case. The information was predetermined. Now look at the right. With quantum particles, nothing is decided until you look. The very act of measuring one particle instantly forces the other one into a corresponding state. You're not revealing a pre-existing fact. Your measurement is creating the fact in that very moment.
So of course, this leads to the big question, right? The one that really bugged Einstein. How do we know it's genuinely spooky? How do we know there isn't just some hidden information, some hidden rule, like with the gloves, that we just haven't discovered yet? And how on earth could you even test for that?
Well, it turns out you can test for it. And they did. The definitive answer came from something called Bell's theorem. Basically, the ultimate test that finally settled this whole debate once and for all.
The logic here is actually pretty brilliant. So first, you start by assuming Einstein was right. You say, okay, let's assume there are hidden rules, just like with the gloves. Then you design a mathematical test. These are called Bell's inequalities that sets a limit. Any system following those hidden, classical rules has to stay under that limit. But then you run the experiment with thousands of actual entangled particles. And what happens? Every single time, the results blow right past that classical limit. They break the rules. The only possible conclusion? The spooky connection is real. There are no hidden variables.
Now, I have to make a really important point here. Does this mean we can send messages faster than the speed of light? It seems like it, right? But the answer, which might surprise you, is no. Even though the connection is instant, you can't control the outcome on your end to send a deliberate message to the other side, so it doesn't violate that cosmic speed limit. What it does do is reveal this incredibly deep, fundamental connection that's just woven into the fabric of reality.
All right, so if we can't send secret messages with it, what's the big deal? Well, this is where it gets really cool. We're moving past the theory and are now actually figuring out how to put this spooky connection to work.
I mean, the potential here is just massive. Take quantum computing. You can entangle quantum bits or qubits to perform calculations at speeds that make today's supercomputers look like pocket calculators. Or quantum cryptography, where you can use entanglement to create perfectly secure communication. If anyone tries to eavesdrop, the fragile entangled state breaks, and you instantly know you have an intruder. And yes, even a type of quantum teleportation is possible, not beaming people around, but perfectly transferring the quantum information state of a particle from one place to another.
But, as you can probably guess, trying to build technology with something this delicate and, well, this weird, is incredibly difficult. Let's take a look at the very real hurdles that scientists and engineers are up against right now.
This table really gives us a great snapshot of the main challenges. Researchers are trying to create entanglement using all sorts of things. Particles of light, tiny superconducting circuits, even individual atoms held in traps. But the number one enemy for all of them is something called decoherence.
You can think of it as the quantumness of the system just leaking out into the environment, causing it to lose its special connection. On top of that, you have constant background noise and interference, plus the huge challenge of just building these things bigger and bigger. It's a massive engineering problem. So really, the whole race to build a quantum future, whether it's computers or networks, it all comes down to solving these fundamental problems: beating decoherence, filtering out noise, and figuring out how to scale up. This is where all the big breakthroughs are happening as we speak.
So, after all of that, what is the big takeaway? What does our entangled future actually look like?
It's this. This is the whole point. What started as a philosophical puzzle that baffled one of the greatest minds in history has now become a real, tangible, foundational resource for technology. Just like we learned to harness electricity or engineer silicon, we are now finally learning how to engineer entanglement itself.
And that leaves us with one last huge question, doesn't it? We've gone from being mystified by this spooky action to actually engineering it. So now that we can build with this fundamental property of the universe, what kind of future are we going to create? What problems that we once thought were impossible are we now going to solve? That is the entangled future we're just now starting to build.